Before I go on to example 3, I just want to clarify something about the graph in example 2. While I did do a bit more investigating, I just want to say that yes, we definitely do have a horizontal asymptote at 4 on 3. So our graph is going to head off here to 4 on 3. It's also going to head off to 4 on 3 down at negative x values. The points of discontinuity, this 4 minus 5x minus 3x squared, the places where that is equal to 0 actually require us to use the quadratic formula, the minus b plus or minus square root b squared minus 4ac all over 2a, and they're not nice numbers at all. So I think when you do graph this, one is here, not too far into the positive side, and maybe down here a bit more negative is the other x value of discontinuity, the places where this denominator would be 0, and hence the graph doesn't exist. And I think that I just wanted to clarify that the graph, I think, does this approaching there and this approaching there, and it has quite an unusual graph here in between those two, and it does something really unusual. This is not a nice upside down parabola at all, and maybe that's where the oblique asymptote comes in. But you wouldn't probably be asked, even in this course, to graph something like to graph that particular one. We will actually see some that look very similar to that, that you will be asked to graph, and yes, I'll definitely point those out as we come to them. I also want to talk about the algebraic form of the function. So here we can see that our fraction is made up of numerator and denominator, obviously, but in particular where the powers of x are actually the same. In the highest power of x is the same. So we've got an x squared in the numerator and an x squared in the denominator. Now, in this case, it worked nicely. It did give us a limiting sum. The y values are heading off to a y value. Never get there, never get to 4 on 3 or 1 and 1/3, but the graph is approaching that value. In the next two examples, you're going to see something quite different happening, and we'll be able to see there's a difference algebraically in what the actual function looks like algebraically. So let's move on to that. In example 3, now we will make note of the actual powers of x in the numerator and the denominator. So you can see here in this example, the highest power of x is actually in the numerator. So there's an x squared in the numerator and only an x in the denominator. Now this is just something I want you to keep in the back of your mind. Our little rule for investigating the behaviour of this graph as x approaches plus or minus infinity is to divide through by the highest power of x in the denominator, and that doesn't change. That will not change, even though the highest power of x is actually in the numerator. So we go through the process. We're going to look at the behaviour of x, or what y value it's heading towards as x approaches plus or minus infinity. So we do this limiting thing, and we divide both numerator and denominator by the highest power of x in the denominator. And you can see then that gives us the limit as x approaches plus or minus infinity of x minus a 1 on x over a 1 minus 4 on x. Applying that limit, we're going to apply the limit now. So rather than, this is not going to naught, this is going to go to either plus or minus infinity. But we know that when you put x to plus or minus infinity in the format 1 on x, that goes to a naught. 1 stays as 1, has no x component, and 4 on x goes to naught as well. That simplifies to plus or minus infinity. It's suggesting here that it's not approaching a value, something similar to we saw in the previous example, the 4 on 3. Or we've seen before, you might approach 0. In this case, the graph is approaching plus or minus infinity. We should have established back here, and you can see I have written it, that in this function, the graph will not exist at x is equal to 4 because that would give us a 0 in the denominator. So we've got our vertical asymptote at x is equal to 4. We know that this graph is going to go off to plus infinity, and it's going to go off to negative infinity as x goes to plus and minus infinity, respectively. Interestingly, this graph comes in, and if we were to investigate getting closer and x values getting closer and closer to 4, we find that the graph's going to go off to infinity as well. And here, the graph is going to go off to negative infinity as we approach 4 from this side. This is giving us this concept of this oblique asymptote. It's like, I guess I shouldn't curl that one back quite that much. So this is going to go along more like that. Let's see if I can get rid of that bit. And this one is also going to go along more like that. So yes, it's going to go eventually to negative infinity and plus infinity eventually, but we've got this thing called an oblique asymptote. Now, that is part of the Extension 2 course, I believe. These oblique asymptotes are not part of the Extension 1 course. You would not be expected to be graphing this. Sure, you might be asked to examine the behaviour of this function as it goes to plus and minus infinity, but you wouldn't be asked to graph it. So, yes, if the question just straight asks, what's the function doing as x approaches plus or minus infinity, you're expected to say the y value is also going off to plus and minus infinity. Okay, now what was happening there? Back to the algebraic format of the function. There was a higher power of x in the numerator. Now, I'm saying this and emphasising this for those of you who eventually will choose to do Extension 2 maths, then you'll need to be looking out for that when you're graphing more difficult functions, when you do that topic in Extension 2. Having a look at then going on to example 4, let's have a look at it algebraically. Algebraically, we're back to highest power of the x is actually in the denominator. So we've got the reverse of example 3, and let's see what happens as we investigate the behaviour of this function as x is approaching plus or minus infinity. And we do that, as we've done with all the examples before, by investigating the limit as x approaches plus or minus infinity. So we're going to divide through by the highest power of x in the denominator, which in this case is the x squared. So that's giving me the limit as x approaches plus or minus infinity of a 1 on x minus 4 on x squared over 1 minus 4 on x squared. Actually applying the special limit that as x approaches plus or minus infinity of this fraction, then that gets replaced with a 0. Over the x squared still approaches 0, gets replaced with a 0. And again, you've got the limit going to 0. Now, you can see there I've actually drawn this going off to 0, and you find that I think on this side it goes off to plus, it goes, we have positive values here. Let me just check that. I'm actually wrong about that. If we were to look at, for example, say x at negative 100. So when x is negative 100, we'd have a negative 100 minus 1, which is a negative, obviously. Negative 100 squared is a very big positive number, very big, and I'm only going to subtract 4 from it, so that's over a positive, and a negative over a positive is actually a negative number, and it's a very big number in the denominator, which means overall it becomes very small. So we're going to head off to 0, but it's going to be negative values, and the graph does do this and it does that. And then here in the middle it does something very interesting, not that we're focusing really on this at the moment, but it actually does this here in the middle, this function. And if I just jump to our GeoGebra demonstration, you can see there now, let me point out, the graph I've just drawn is here in red. So we will go, yeah, it's this one that I'm highlighting, red at the moment. And that was our x minus 1 over x squared minus 4. The blue one was the one that I said was very unusual here in the middle. And that was the one that's got the equal powers of x in both the numerator and denominator, had the x squared. And the green one, which, I can highlight the green, has this clear oblique asymptote. You can go to GeoGebra or any other graphing program that you know and type those function values in and have a look at the graphs yourself to see what they actually look like if that GeoGebra one wasn't all that clear. Okay, so I guess in conclusion we could say that we get nice horizontal asymptotes when the power of the x in the denominator is greater than the power of the x in the numerator. And if we do get the power of the x in the numerator being bigger than in the denominator, we get this oblique asymptote. And when the power of x is the same in both the numerator and the denominator, we might get a horizontal asymptote, and we might also get something very unusual happening around the center.